Problem 9, and in this circumstance the electric field is constant as it moves through the apparatus. So we have voltage of the particle equals E times d, where d is the distance the particle traveled. So while in the apparatus, the charge experiences the force equal to m times a equals q times e. And you can replace E with voltage over d, as seen here. And we can also replace A using motion with a constant acceleration formula, so v squared, meaning velocity squared, over 2d equals A. So once we make all these replacements, we get an equation for velocity equaling this. So while the particle is outside of the apparatus, we can talk about the force that the magnetic field produces, which in this case is QV cross B. But this reduces to just QV times B because V and B are perpendicular. So we have QVB equals mass times centripetal acceleration because the particle goes in a circle while in this field. So then we have QVB equals mv squared over r. And solving this for r, we get this equation. And then we can plug in the velocity that we found earlier into this equation to later get this. And then using that, we can plug in the values for particle 1 and particle 2, as given here. Now we can find a ratio between radius 2 and radius 1, just plugging in the equations that we found earlier. And after some simplifying, we get that the relationship is 1 over the square root of 6. And after we move some things around, we get the radius of 2, which we're trying to find, equals the radius 1 over the square root of 6. And given that we have radius 1, we can just plug that in and then finally get radius 2, which in my case is 0.49 meters.